Well, good afternoon, students. Today I am going to teach you the topic Raman spectroscopy. So, first of all, we will discuss what is spectroscopy. So, as you know, the word spectroscopy is made by two words, spectra and scopy. Scopy is basically study. So, in the spectroscopy, what happened? We study the interaction of matter with EMR, and this EMR is basically electromagnetic radiation. As you all know that the radiation which we are receiving, it have two properties. One is electrical properties as well as magnetic properties. So, this EMR when interact with any molecule, it gives certain information, and this study, this interaction, this study of interaction, it is called spectroscopy. So, basically spectra, whenever the molecule is interacting with any EMR, it is showing two type of spectra. One is either the molecule will absorb the energy and get excited. This is the ground state, suppose. So, it will excited from this to this. And if this kind of spectra we are receiving, this is called absorption spectra. Absorption spectra. Basically, what is this EMR? This is basically energy, and this energy is E is equal to h nu. So, basically this is h nu, okay, where h is a Planck's constant and nu is a frequency. So, whenever this energy or EMR interacting with the molecule, this molecule or electron get excited and reach to the excited level. This kind of absorption of this EMR, it is called absorption spectra. While after some time, it will return back to its original state by releasing, by emitting the same energy which is absorbed by this molecule h nu. So, when the absorption spectra occurs, the h nu is absorbed and the molecule reaches to the excited level, and during emission the same energy h nu is emitted out and the molecule return to its original state. This type of spectra, it is called emission spectra. Okay. So, today we are going to discuss this Raman spectroscopy. The Raman spectroscopy is basically discovered by Sir C.V. Raman, Chandrasekhara Venkata Raman, who got Nobel Prize in 1930 for physics. Basically, this Raman spectroscopy is what? So, it is a type of spectroscopy which deals not with the absorption of EMR, but it deals with the scattering of light by the molecule. And I already told you that it was discovered by Sir C.V. Raman. He discovered when a beam of monochromatic light was allowed to pass through some organic substance, the scattering light contained some additional frequencies over and above that of incident frequency, and this is called Raman effect. So, this is basically written. Exactly what is this? Please pay attention here. First of all, you should know what is the scattering. Suppose you have a light source, this is a bulb, okay, and the light is striking to a wall, okay. So what happens? This is the incident light, this is the transmitted light. Some light get scattered, okay. So this is the basically scattering, and due to this scattering, the color of sky we are looking sometime blue, sometime red, sometime oranges, okay, orange color. So this is due to scattering. So if you will see the scattering is basically divided into two parts. One is elastic, or you can say elastic. When incident light interact with this molecule or charged particle, it is get scattered. So this scattering can be divided into elastic, this collision can be divided into elastic collision and inelastic collision. So what happened? What is inelastic collision? When a charged particle, suppose this is one charged particle and this is my incident radiation, okay, I naught. When it is this incident radiation falls on this charged particle, what happens? Sometime we will get the intensity get decreases, the scattered light get intensity of scattered light get decreases, and sometime the scattered intensity increases, okay. While in elastic collision, what happens? Suppose this is my molecule and some monochromatic light or some light is falling on this molecule, there is no change occurs in the intensity of this light. Suppose I have the incident light is I naught and the scattered light is also I naught, means energy of incident light is, you can say, mu, and this is the frequency of this scattered light is mu dash. So mu is equal to mu dash, means there is no change occurs in the intensity of this scattered light, or there is no change in the frequency of the scattered light. So this type of scattering, it is called Rayleigh scattering. Rayleigh scattering, okay. And this type of collision, it is called elastic collision. While when the change occurs in the energy, then it is called inelastic collision. So inelastic collision is basically related to charged particles and shows just like Compton effect, okay, while this elastic collision is for molecule. So Sir C.V. Raman has noticed that approximately 10 to the power 6 time when a laser beam is falling on the molecule, this molecule will 10 to the power 6 time, it will show just like elastic collision, means there is no change in the frequency, but one time in 10 to the power 6 attempt, what happens? 1 over 10 to the power 6 attempt, what happens? This elastic collision get converted into inelastic collision. What I want to say? I would like to say that one time whenever this is a molecule or a charged particle, suppose this is a molecule and I am falling a laser beam on this molecule. So 10 to the power 6 time it is the energy which is this is equal to transmitted energy. There is no change in energy. But one time what happens? One time of 10 to the power 6 attempt, energy either get reduced or get increased. This type of collision, this type of scattering, it is called Raman scattering. Okay. So basically elastic collision, I have already told you what happened when scattered photon has the same energy as incident photon. This is called elastic collision and it gives Rayleigh scattering. I have already told you that this is my charge, this is my molecule and this is my nu. This is the basically nu is a incident light and nu dash is the scattered light. When this nu is equal to nu dash, this is called elastic collision or Rayleigh scattering. This is called elastic collision or Rayleigh scattering. While in inelastic collision, what happens? This scattering or scattered photon has an energy that is less than or greater than incident photon, which is Raman scattering. Means this is my molecule, this is my incident energy mu, and if the energy get reduced or the scattered light energy get increased, this type of collision is called inelastic collision and it is also named as Raman scattering, which occurs about 1 in 10 to the power 7 or 6 photon. They are inelastic. They are showing inelastic collision. Means 10 to the power 7 time if I am falling a beam, laser beam on a molecule, then one time, only one time, elastic collision get converted into inelastic collision. Okay. So one time what happens? The scattered light energy either will be increased or decreased. So this is this conversion of elastic collision into inelastic collision. This is basically Raman scattering. Okay. So this is showing this what? This is this line. It is Rayleigh scattering. This line is Rayleigh scattering line. While on the negative side, we are getting Stokes line. On the positive side, we are getting anti-Stokes line. So I am going to discuss exactly what is Stokes line and anti-Stokes line. So this is very important concept. Kindly pay attention. So suppose this is, and this is also related to the one important theory, which is you can say it is a photoelectric theory of this Raman. So this is a molecule, and when the molecule is interacting with a new energy, what happens? Either the energy will go to the molecule, some part of the energy will be absorbed by the molecule, or if the molecule have more energy, then it can transfer the energy to this incident radiation. Only two possibilities are here. So, one possibility I am going to discuss. Suppose I am giving one laser beam or one monochromatic light having new frequency to a molecule, and the molecule absorbs. It will absorb some energy from the incident light, then the scattered energy will be less. Okay, and this is suppose nu dash. Okay, so nu is higher than nu dash, and this type of line we are getting, this is called basically what? Stokes line. Stokes line. Okay. So what I would like to say, when energy is transferred, from radiation to molecule, so resultant frequency get lowered than the incident frequency. So this is the incident light and this is the scattered light. Okay. So the incident energy will be higher than the resultant energy, or you can say scattered light, and this type of line on a spectra is named as Stokes line. Okay. It can be defined in another representation, that is this graph. Suppose my molecule is here. Okay. This is basically ground state, and some energy it is receiving, it get excited and reaches to a virtual state. Some virtual energy level will be here. It will reach to that energy level. After for an instance, it will return back to its original position. Okay, by emitting the same energy that have been absorbed. So the incident light here is nu naught, or I can write down it as nu, that is equal to emitted light, which is again nu naught or nu. So this type of scattering, it is called Rayleigh scattering, which is elastic collision. No change occurs in the incident energy and observed energy or scattered energy. Okay. So this is called Rayleigh scattering. Suppose another case that I had discussed here, it is represented like this also. My molecule is here, it is getting one energy, that is h nu naught or h nu, and it reaches to the one virtual energy level. Okay. So during this interaction, what happens? The energy is transferred from this energy to the molecule. Hence, the resultant energy get reduced and the molecule is returning, and due to less energy, it get stagnant here. Okay. So the energy that is incident, the energy which is observed, there is a difference, and this is called basically Stokes line or inelastic collision or Raman scattering. So same thing here, like molecule is receiving energy from this monochromatic light, the energy of the molecule get increase and it get excited, reaches to a virtual state. But when it is returning, okay, what happens? The incident light that have been reduced here. So, the energy of this get reduced, that's why it will stagnant here, some upper energy level, and this type of lines are named as Stokes line. Okay, I hope that I am able to clear you. Next, what is the anti-Stokes line? I am going to represent in a both a way. Suppose this is my molecule. I am giving one EMR or laser or energy in a form of mu. Now, the particle have also some energy, higher energy. So, the energy is transferred from molecule to this incident light. So, what happens? The resultant energy get increase. Okay. So, this nu dash get increased, and this type of line, it is called anti-Stokes line. So, here what happens? Nu dash is higher than nu, and this is called anti-Stokes line. Okay. So, what is the basic difference in between Stokes line and anti-Stokes line? Here, the energy of the molecule is very low. It receives the energy from energy source. Hence, the transmitted light get decrease. Okay, and this is the Stokes line. Here, the molecule energy is quite high, means the molecule is already at excited level, and it transfer its energy to this incident radiation. So, the scattered light energy get increase. So, this is the anti-Stokes line. So, by this representation, I would like to explain again. Suppose the energy is high. So, my molecule is placed here at higher energy level. Here the energy is high, that's why my molecule is at higher level. So, this, when it is interacting with this h nu, what happens? It reaches to a virtual energy level, return back to this, but because the energy is also increased here, so the incident light which is quite higher now, it is the molecule return back to the quite lower energy level. So, this is the lower energy level. Okay. So, what happens? The energy that is scattered here, it get increases. So, how much increases? This much increases. Okay. So, this is basically anti-Stokes line. Okay. So, what is the impact of this line, Raman lines? These Stokes line or anti-Stokes lines are also named as Raman line. So, what are the impact of this Raman lines on room temperature as well as when the temperature is increases? So, suppose this is my basically at room temperature I am going to discuss. So, mostly molecules are populated here. Okay. Very means at the ground energy level, mostly molecules are populated. Okay. So, at room temperature, what happens? More intense Stokes line get observed. Okay. While at room temperature, very less molecules are at the higher energy level. So, at room temperature, anti-Stokes lines are quite less intense. Okay. Because the molecules are too much at the ground energy level, hence their interaction will be increased. Their interaction will be increased means they will show more Stokes line. they will show more Stokes line. Okay. So, the population of Stokes line get increased at room temperature. Okay. So, intensity of the Stokes line on room temperature get increased. Okay. While very less molecules are higher energy level, very less molecules are here which are less populated, hence their interaction will be less, hence they will show very less, you can say, spectra, and their intensity will be less. Okay. But if I am increasing the temperature is increases. So, if these are the molecules, suppose, and I am giving some energy, some temperature also. So, the molecule also get excited. So, maximum molecules reach to the higher energy level. Okay. And very less molecules remains in the ground state. Suppose there are 5 molecules. So, when I am giving temperature, I am increasing the temperature, 1 molecule is here, while the 4 molecules reaches to the excited higher energy level. So, it will give what? Stokes line. How? It will reaches to this point, return back to here and stagnant here. It will give Stokes line. So, the intensity of the Stokes line is due to this molecule only, which is less populated. Hence, the intensity get reduced. While more molecules are on the higher energy level, that's why they will reach to a particular virtual energy level, not stagnant here, they will reach to this point. So, the energy will increase. Hence, the intensity of anti-Stokes line get increased. So, in a brief, I can discuss that intensity of Stokes lines at room temperature are high and anti-Stokes line intensity at room temperature are low. While I am increasing the temperature, then what happens? The intensity of anti-Stokes line get increases, while intensity of Stokes line get decreases. Okay. So, basically this Raman scattering is basically dependent also on the polarizability. So, kindly read it as polarizability. What is this? Suppose this is my molecule and there is no permanent dipole moment in this molecule. So, what happens? Permanent dipole moment is absent, it will not show IR spectra. It is also inactive in, you can say, it will not interact with the spectroscopy. Okay. So, once this molecule is placed in a, you can say, electric field, and the direction of the electric field is this. This is the plus side, this is the minus side. So, this is suppose electron pair. This is electron pair. What happens? When I have placed this molecule in a electric field, what happens? The electron get repelled from this pole and get attracted to this pole. Means the dipole moment get induced. Means this electron is shifted to this side. Okay. So, some dipole moment get induced, and this is how easily this electron can be moved from poles. This is called polarizability. Okay. So when an electric field is applied to the molecule, its charge distribution gets distorted. This induces a dipole moment mu in the molecule, and the magnitude of the induced dipole moment varies linearly with the strength of electric field, which can be weak, which can be higher. If this electric field is weak, then induced dipole moment will be quite differ. If this will be high, then they will be quite differently behave. They will behave differently. Okay. So it could be mu is equal to alpha E, and this alpha is basically polarizability. This alpha is basically polarizability. So this alpha is the proportionality constant, which is denoted as alpha. It is called polarizability of the molecule, and this alpha is measured how easily it is to distort the charge distribution of the molecule. This alpha depends on the direction of electric vector relative to the axis of molecule. Hence, it is tensor quantity. And also, if the bond, suppose there are sigma bond, then the sigma bonds are quite stronger than pi bonds. So if I will place this electric field on sigma bond, so there is a distortion will be quite low. So such kind of molecule that have sigma bond, it is called hard molecule. Okay. And those molecules in which distortion can be easily done, then this type of molecules are called soft molecule. Okay. So the molecule must be anisotropically polarizable. So what is this anisotropically polarizable? Iso means same. Okay. And tropic means arrangement. Okay. So if the molecule is rotating, suppose this is my molecule, H and H, this is my molecule. Okay. And it is rotating. I am going to discuss here Raman spectra with reference to rotational spectroscopy. So the movement could be like this, then like this, then this, and finally, suppose this is A molecule, this is B molecule. So this is A molecule, this is B molecule, again this is B molecule, this is A molecule, and the last which comes again to the A molecule and B molecule, this is H, this is H. Okay. And this is my electron pair. So if this molecule is rotating and it is placed in electric field, what happens? The distortion could be high here, okay, less here, again higher, again less. Okay. So you can see the arrangement is not same. Arrangement is not same. Hence, it is called anisotropic. Okay. And isotropic, if the arrangement is same everywhere, then this is called isotropic. So that's why the molecule must be anisotropically polarizable. The polarizability should be anisotropically. Okay. So spherical molecules are isotropic polarizable, and therefore they do not have rotational Raman spectra. If the isotropism, isotropic, you can say polarizability is there, then it will not show any induced dipole moment in the field, in the presence of electric field. Hence, it will not show rotational Raman spectra. While all the linear molecules which are anisotropically polarizable, they give rotational spectroscopy. Okay, they give rotational spectroscopy. For example, oxygen, which is homodiatomic molecule and doesn't show dipole moment. Okay, but when placed in electric field, or it show anisotropic polarizability. Nitrogen, hydrogen, we don't have pure rotational spectra, but they will show, they can study in the Raman spectra. So here I am going to show the same thing. The oxygen, this is the isotope of oxygen, oxygen 18, 16, and now it is rotating. Suppose this is basically external electric field and this is the rotation of dipole. So here is the lone pair. So electron can be easily distort in this direction, while here electron cannot distort. Again here electron can distort, cannot distort, can distort, cannot distort. Okay. So this type of the induced dipole moment arrow we will see here: maximum, very minimum, maximum, minimum, maximum, minimum. Okay. So when a molecule is subjected to strong electric field, then what happens? The field will be distort the molecule electron charge distribution to induce a small dipole moment, which gives, or you can say, which is proportional to the electric field. Distortion will be equal to the intensity of the electric field. So this is mu induced, means dipole moment induced, which is directly proportional to the external field, which is E. Okay. Okay. So I think the basic point we have discussed, that how the Raman spectra is originated. Now I am going to discuss the mutual exclusion principle. Mutual exclusion principle says that for centrosymmetric molecule like hydrogen, oxygen, nitrogen, carbon dioxide, in which with respect to center atom the distance of both the atoms are same, these are the centrosymmetric molecule. So for those, the given molecule that possess center of symmetry, the vibrations which are IR inactive, they can be studied in Raman, or they all are Raman active. So those vibrations which cannot be studied in IR spectroscopy, though those vibrations can be studied by the Raman spectroscopy. For example, here hydrogen, oxygen, nitrogen, they don't have dipole moment, that's why they are IR inactive, but some of those vibrations which cannot be studied by this IR, they are Raman active. Carbon dioxide, that show symmetrical stretching. Carbon, this is carbon, this is oxygen. Okay. So this type of, if this stretching is same, then this is called symmetrical stretching. So in a symmetrical stretching, no dipole moment occurs, hence it is IR inactive. But these type of vibrations which are symmetrical stretching, which are showing symmetrical stretching, these type of vibration can be studied by the Raman. CO2, that shows asymmetrical stretching due to dipole moment, they are active, but they are inactive in Raman. Carbon dioxide bending, They are also showing change in dipole moment, hence they are active in IR but inactive in Raman. So I hope that I have cleared some doubts of this topic, Raman spectroscopy, in which most important thing is Stokes line and anti-Stokes line. In Stokes line, energy of the molecule is less, hence it absorbs the energy from incident light. That's why scattered light get reduced. While anti-Stokes line, the energy of the molecule is high, hence it gives energy to incident light, then that's why intensity of energy get increase. So I hope I had cleared it. Thank you very much. Thank you, students.